So since we spent so much time over the last couple lectures talking about sinusoidal waves, I thought it would only be appropriate if we talked about sinusoidal traveling waves. Okay, so first of all, what does a sinusoidal traveling wave look like? Hold on, I'm going to have to exit here because I have a cool little thing. Woo, generic background, yay! Okay. So basically, this is what a traveling sine wave looks like. It just looks like a sine wave that is literally marching along, traveling in time. So that's what we're going to be talking about right now, okay? There's three things because we're going to come back to this applet in a second and do cooler stuff with it. But let me do this for now. And back into my slideshow. Okay. All right. So I want to point out something. Let me see if we're not quite there yet. Okay. So these are some snapshots of what this traveling wave might look like at various times t. Now, if we imagine that we look at one particular x value, let's put a little dot on it, and we look at what the motion of that dot looks like. So right now we're looking at one fixed x value evolving in time. It's going to kind of look like this. Excellent. I like the dance move. Okay, so you can see that it's oscillating, right? So at a fixed position t, this point oscillates in some time big T. So do I have another chalkboard back here? Oh no. Okay, so it repeats. It repeats itself. Okay, so what the heck does that mean? It means that if we start with the equation that we're given up there, it means that the wave function at some position in time has to be the same at that same position, but at some time t plus big T. I'm making up big T right now. It's some time at which it repeats itself. So if I write what that equation is both these times, so I write a sine of I'm just gonna, okay. Okay, so the only way that these things can be equal is if this constant k, which is not the spring constant. Sorry, can you guys even read that? Let me rewrite that. Is that no better? Okay. Oh, I would not be very good at CS then. Okay. 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 The only way these guys can be equal, see, they each have a term kx that's identical. They each have a term vt that's equal, little t. They each have a phi naught. The only thing this guy has that guy doesn't have is kv big T. So what must kv big T equal? It better equal 2 pi n. So I'm just going to, let's say, equals 2 pi. Okay, so that tells me that my period, the time it takes for it to repeat itself, is 2 pi over kv. So let me stop right here because I want to make sure for a second. K is not the spring constant. K is not the spring constant. I want everybody to say that.
K is not the spring constant.
Okay, thank you. 1 second, Marcy. The reason that we stick it in here at all is because x plus vt, what are the units of that? Distance, right? So we can't take the sine or cosine of that directly. So we have to multiply it by something that's going to make it unitless. So what are the units of k going to be? 1 over distance. So remember, k from the spring constant has units of force per meter. So these even have different units. So they can't be the same thing. Okay, Marcy, you had a question.
What does k actually mean? Is it just units or is it a number?
For right now, we're saying it's for units, and in a second, we'll talk about what it physically is. Okay. So we already talked a lot about harmonic motion, things oscillating, and we had a relationship for a period in terms of angular frequency. And we said that t is equal to 2 pi over omega, where this is the angular frequency. So that means that we can say that the angular frequency of this oscillation is kV. So that means we can rewrite this guy like this. Okay? So now that was looking at it for a fixed time. So, sorry, for a fixed position. But now if we look at it for a fixed time, we can see that, again, this wave repeats itself over what we call the wavelength. We're going to call that thing lambda. So that means if it's moved, it just, that means that kx, if x is lambda, what must it equal in order for this thing to repeat itself at a fixed time? So if we know that this function when x equals some x naught plus lambda, we shift it over by some lambda. In order for this thing to repeat itself, we must get that k times lambda has to equal 2 pi. Right? Because we have k times x up here as the argument of sine. If t is fixed and all this other stuff is just a constant. So in order for it to be equal when you evolve by some position lambda, that has to be equal to 2 pi. So that tells us that this thing k is just 2 pi over lambda, where lambda is the wavelength. So to summarize that all up, here are all the physical parameters that go into sinusoidal waves. Whoa, I'm going to leave this up here for a second, and these will be posted. So, what just happened? Oh my gosh. Okay, so what I'm telling you is that we're giving you the equation for a sinusoidal wave, right here, and I'm just rewriting it in a number of ways to show different combinations of these variables and to show what they mean physically. So A, well, that's just the amplitude. This V that's in here, like in all the waves we've done, those are just the speed of the wave. Phi naught, that's just the initial phase. I choose to start my dance from here or from here, right? So it's just the same thing as in the oscillations. K is what we call the wave number in 1 dimension. In 3 dimensions, it's the wave vector. It points in the direction of the wave propagation, but we'll leave that for a later course. But for now, it's just the wave number, where it's given by 2 pi over the wavelength. The wavelength is how long in space the wave is before it starts repeating itself. Okay? And then this wave has an angular frequency, which is k times v, where v is the speed of the wave. Since k is also 2 pi over lambda, you can write it that way. And omega is 2 pi over t still. And now I'm going to introduce some new character called nu, which looks shockingly a lot like a v. I promise you it's not a v, it's the Greek character nu. Nu is just the plain old frequency. It's not the angular frequency, it's just the frequency of the wave. And we can see from these equations that it's given by nu times lambda equals the speed of the wave.